Okay, well, thank you very much. So my name is Emilio Guzman. I am the leader for Mexico. We cover the whole continent in the look for alternate components, which is practically crosses, uh, technical questions, and we have a lot of communication with the whole offices around the world from Wurth Electronics. And today we'll talk to you about the pressit technology and its high current applications, and why it is the best solution for power delivery. So the objective today is to teach you about the REDCUBE series. And let's take a look at the agenda today. First, we will learn how the technology works, then the electrical properties like its current density. After that, the details regarding the PCB like surface tolerances. Then the processing, here we'll see more detail about the actual press fit process and some hints. And finally, some application examples. And so let's start with what the press fit technology basically is square pins that press into a round via, which creates a solder-free, gas-tight, and powerful electrical connection. Due to this component's material, shape, and simplicity, it can withstand more mechanical, electrical, and environmental effects than any other termination. It's a main glass block with thin plating. It has pins that deform into the via, molding the trace and extending them vertically to terminate the connection as one. It requires no additional material resistivity from solder joints, and it's designed without any temperature sensitive or brittle material such as plastic. And so the usage connector can land anywhere where the usage is very rough and the environment is very demanding as well. But there's a key word here, which is Gastight. Why Gastight? What does it mean, and how does it work exactly? So a Gastight connection is achieved thanks to a cold welding process, which is when two metal surfaces are friction fit together. The molecular structure of the surface is stressed by the force needed to press the pins into the vias, and needs about 48 hours maximum for the molecules to restructure in an ideal balanced way. So during the cold welding process, the junction between the brass of the power element and the copper of the via becomes an absolute homogeneous and gas-tight connection, which has a very low contact resistance and high mechanical retention force. The pin surface provides a smooth sliding into the via and is pressed to the sides, creating an additional sealing around the connection. So let's talk about the advantages of the press fit technology actually. So first of all, it's low resistant connection, which is around 100 to 200 microohms, which means low self-heating, and so less heat must be dissipated through the system. So low heat will go to the rest of the PCB, very low heat, and less heat dissipation will be needed. So right away, this is a great advantage for this technology. The fact that the heat transmission to the rest of the PCB will be greatly reduced means that the application will last much longer without degrading any other components. Also, no problems with cold solder joints. This is a crucial topic when we're talking about different materials sandwiched together, which also have different thermal expansion coefficients, and which we will get more into detail later on. Also, no heat development in sensitive components. And as I said, This is a complete metal connection. There's no heat will transfer to any plastic or any other material. Even getting up to hotter temperatures, there will be no damage on the connector. So another thing is that it is mechanically more stable than solder connections. And as I said before, the metals are fused together and cold welding is stronger than the usual solder joint. Which also leads to a high mechanical holding forces. So it is useful for tough environments where the connection might be subject to external forces. Also a very high ampacity, it can hold up to 300 amps, which is around 10 amps per pin. Then the double-sided mounting of circuit boards is possible. And it is also very durable. So it's a high quality connection with a failure in time value of up to 30 times better than solder elements. And it is suitable for rough usage and environment conditions. And so here we can actually see the advantages that we are talking about. So on the top two images on the left, the high mechanical stability and holding forces capability along with a space-saving design for a technology with such a high ampacity, well, it's very practical. And you can see in the image, you can get up to a really high transmission of energy in such a little space, just with the REDCUBE connector and the cable lug. And so on the bottom left, there will be no problem with cold solder joint. There will be no bridges creating a short or other problems. There you can see just the solder joint came between the two pins, and well, that would create a lot of problems for your application. And so with the REDCUBE connector, you wouldn't have that. On the two images on the right, there are no plastic or sensitive components on the REDCUBE connector. So there will be no plastic melting due to high ampacity. And again, it is a solid piece of metal with no plastic at all. And so where is the pressit technology used? Well, it's commonly used in high current on the PCB, either a permanent or constant load or a peak current. With a high mechanical stability, you can imagine a big hardware or something, an application with a very big tension or shearing forces, or a rough application, simply put like that. A high environmental stability, because it can hold up to really high temperatures and vibrations and harmful gases. So it is a very, very robust system. And also to mention, the REDCUBE will support currents up to 3 amps, as I said, while the terminal block can only support currents up to 57 amps. And well, the REDCUBE connector with the plus side of being space efficient. So let's examine the usage of these REDCUBE connectors in the electronics PCB of a bus, let's say, or nowadays with the green or electric approach for vehicles. The REDCUBE high current capability will come in very useful for power delivery. Imagine an electric car peaking very high currents during a fast acceleration, or a bus managing high currents along an extended period of time. So those are just some examples, but in general, any kind of approach where there is high power, this connector will perform very well. And moving on to the difference between the massive and flexible pins, which you may have seen before. There are advantages to massive pins. Massive pins are our REDCUBE pressit technology. And so there are advantages over the massive pins from over the flexible ones. Würth Elektronik does not sell the flexible ones anymore though. But in this slide, you can see how the two technologies compare regarding the press fit zone. So on the top left, we see a cross section of a single massive pin that presses into the via. And there are 4 connection areas. So the 4 corners will make a connection with the via during the press fit process. On the bottom left, we see a close-up, a zoom on the corner of the pin. So the tin is displaced to the outer side of the contact area. And so a homogeneous junction from brass to copper is made. And on the top right, we see the flexible pin pressed into the via, and the pin has narrowing in the middle, and the shape is not straight, more like oval. And on the bottom right, we see the deformation of the pin during the press fit process because of the narrowing. So both connectors. So on this first image, you can see this is the connection that the REDCUBE connector would make with the PCB. So it's a complete corner of one of the pins, which is shown here in the bluish color. And then in red, we can see the contact area of the flexible pin shown in red. So we can see that it is much smaller than the connection that the REDCUBE pin may be able to make. Now we can see that there is 1/2 of the THR connector. So even though it is bigger in size, it has a smaller connection. Now see the via here on the image that just appeared, and this would be the simulation of a flexible pin that presses into the via, and another view that shows that the connection area is shorter than the length of the via. So there we can see the actual deformation of the THR pin, which only makes connection in the little area in yellow at the sides. And because of a small contact area, the pull-out forces will be smaller, and the current carrying capacity is also smaller. Although there is no cold welding process because of the low forces. And the benefit with that would be that there would be no deforming of the via on the PCB, and nearly not existent because of the PCBs. The pin is deformed. So if the pin of this is deformed, the PCB will not be. So that gives possibilities for connection, like fast on connections, but still the current capability is smaller. And so in this image, we can appreciate the average connection angle of the massive pin. Normally, in average, we get about from 10 to 15 degrees of connection angle, but you can see that only the corners make contact with the PCB. But that is more than enough, and you'll see why in this next slide. So this is a proof of concept of the contact area for the PCB, and one contact angle of one corner is an arc. So it's part of a circle line, and we calculated with 2 times r times pi times alpha divided by 360 degrees. And additionally, we need the length of the connection area, which for a massive pin is the PCB thickness, called L in this case. Due to the fact that one pin has 4 corners, so the factor 4 is added. This leads to the first formula on the first line. In the second line, we fill this formula with numbers. So we suggest a PCB thickness of 2.4 millimeters and our average angle of 13 degrees, which I just showed you on the last slide. And so with that, we can calculate the radius from our pin dimensions, which would be of 0.725 millimeters. Then in the third line, we multiply by 4 because of the 4 corners. So what is the result with all of this? With our calculation, we show that the connection area of the via is bigger than the diameter of the pin. This means that the pin itself can carry less current than our connection area. So I'll repeat that again. This means that the pin itself can carry less current than our connection area. So there would be no problem at all with the connection to the PCB. And so the ratio will be better with a thicker PCB and lower with a thinner PCB, but it will still be perfectly okay. Additionally, the specific conductance of copper is 4 times better than for brass. So this means that an average angle of 3 degrees would be enough to provide that the current can be carried by the pin and can also be carried by the contact area of the pin. And so here is an animation of this previous calculation that I just showed you, which is loading. And so for this, we can see that here the pin is the via, and if we unfold that connection, we can see the 4 corners making contact with the PCB. And so along those 4 corners, the current flows from the connector to the PCB. And now if we divide, or if we select only the connection area, we combine them together, the connection of the 4 pins, and then we add them to the thickness of the PCB, we can see the difference of what I just explained to you. And so moving on to the pin efficiency, the difference of a cluster and a different arrangement of the pins. And so here we can see 2 very different arrangement of the pins, and therefore 2 different efficiencies. Having the pins together in a more confined and closed space will create more heat, thus reducing the efficiency. The one on the right with a space in the middle, so with a sometimes there has a hole for the connection itself. The one on the right will allow the connector to dissipate more heat and have a better efficiency. So on the left, we can see that the pins are all close together, and that would create a bigger heat concentration for the connector. So just in the middle, there would be a lower efficiency, and the connector by itself would have a lower efficiency than the connector on the right, than the arrangement of pins on the right. Now this is really interesting. We can see a current density through the pin, through the pin itself. So let's imagine the current is flowing from the right to the left of the pin. And now this yellow part is the PCB. If we add the PCB layers to the pin, we can see that there's more current passing through the first and last layers. So the first layer will take more current, and the next layers will experience less current flow. But there is something really interesting. Why is the last layer from right to left? Why is the last layer suddenly peaking a little bit in current transmission? Well, the little piece of the pin that comes out of the PCB at the end, so at the bottom of the PCB, let's say, it is able to dissipate a little bit of heat. And because this pin peaks out just enough to dissipate a small amount of heat and increase its efficiency, the two middle layers decrease its current flow because they are sandwiched together, increasing the heat. So this is a very interesting approach, and very interesting to see how the pin reacts to the different copper layers. And now let's move on to the failure in time value. So the frequency of failure of the press fit parts is decreased compared to the one that is soldered because of the tolerances. So if we see on the left the THR, the pin floats and has less resistance on one side than the other. So the current will flow differently than with the press fit technology on the right, where we see a very light deformation of the copper traces, but the contact is symmetrical with all different layers of the PCB. And so let's just pause for a minute. As we see on the left, you can see the solder is more concentrated on one side than the other. So this will create a different conduction of current. While with the press fit, we'll see that although there is a minimal deformation on the PCB, the connection is flawless between both sides and homogeneous and symmetrical. So now there is an issue with cold solder joints, which I talked about in the beginning. And so when the process is done, there has to be a proper heat source so that the solder is made successfully. For THR, this is the case. We'll see about press fit in a second. With the image to the right, you can see a separation between the pin and the solder due to several factors, including thermal expansion, and the THR is a valid option, but making the process automatic has its limitations. And so as you can see in the image, there's a separation between the solder and the connector itself. And so the major problem with that, with a gap, is what we see here. So a gap would eventually create a spark, so practically a short, and that eventually burns. So you don't want this on your application, of course. You don't want a burning PCB. So should you consider soldering the press fit connections? It sounds like a good idea, right? But it actually isn't. By soldering the press fit connections, most of the benefits of the press fit technology will get lost. So the contact resistance, the mechanical strength, and all the other advantages that we saw in the beginning will get lost. So this is a very important part of the technology, that due to the volume of the REDCUBE press fit elements, it is hard to bring it to an overall temperature that allows to realize a good solder joint. And it takes away heat from the process. So this can affect soldering of parts placed close to the REDCUBE press fit elements on the PCB. So a lot of the heat will actually go to the rest of the PCB and not actually to the connector, because we have a huge piece of brass which is absorbing the whole heat source, and it's just practically transferring it to the rest of the PCB. So it is not a good idea to solder press fit connections, because there are worst cases that can happen due to it. And so another thing is the process safety and verifiability. And so there's another issue with the heating effect, which is on the plating itself of the connector. So the plating might be peeling away. Heating the REDCUBE connector, the REDCUBE press fit element, can lead to thermal expansion, which weakens the press fit connection. So it can also lead to melting of the thin surface, and the tin can accumulate in the thread and make it unusable. So it is a big effort to ensure also that the vias are filled up with enough tin constantly. And if they are not filled completely, you will create a short, as we saw in the image before. So it is a big effort to try to fill the press fit connections, and if they are not filled, it may be even worse. And so we talked about the connector itself, but how do you choose the correct cable log? So this table shows what current is specified for which diameter at a certain temperature. In this case, either 20 or 50 degrees, and which size of cable logs fits to those cross sections. So if you stick to this table and take care about the rating, there will be no problem with the current carrying capacity on the REDCUBE press fit technology. And so what specifications are you going to need for your PCB? You have your initial untouched PCB. You start with that. Then you can drill the hole, and the hole should be 1.6 millimeters in diameter. Then then goes the copper deposition. A layer between 25 and 60 micrometers should be fine, but the optimal amount is between 30 and 40 micrometers for the best results. This will eventually fuse with the brass from the REDCUBE, so this is a very important part. And after the thin plating, it will gain of 15 micrometers, but of 2 micrometers. Although the thin plating has some important specifications as well, which we will see. So there are these two processes for plating the PCB, the connection for the PCB. One is the electroplating, which is the chemical thin plating. And here, as you would know, the item is connected to an electrical circuit, forming the cathode, the negative side of the circuit, and while an electrode, typically of the same metal to be plated, forms the anode, so the positive side. When the electric current is passed through the circuit, metal ions in the solution are attached to the item. And well, to produce a shiny surface, the electroplated sheet is then briefly heated above the melting point of tin. And then there's the other method, which is hot air leavening, or HAL. So this would be dipping and then flowing off the residual, which is where the PCB gets dipped into the molten solder, and then the excess is blown off with air. And here in the images, you can actually see very clearly the difference between these two methods. So with the chemical tin plating, you can see that the thickness of the plating is very constant, is very well done over the whole surface that wants to be plated. Now with the hotter leveling, the surface is not evenly plated. So you might see concentrations of the plating uh, smaller on some parts than others. So we actually recommend the chemical tin plating for the press fit process because they said it provides a better surface. And far diameter for so as you can see, the tolerances may be different because of the processes, and you might need to adjust the design of your PCB previously to allow the correct treatment for your PCB. So the design and so a square cross section of the press fit technology carves into the copper traces. So the corners carve into the copper traces, uh, making the connection and not the entire wall, like with a rectangle, let's say. Tin helps lubricate and protect against the oxidation when the pins are pressed into the via. So tin plays an important role in this process. And as you can see with the rectangle shape, there would be more deformation on the PCB. So that may not be desirable for your application because it may deform maybe some components around it, and you might not want that in your application. And with the press fit technology, we can just carve through the corners and there's a minimal deformation. And so the different types of the knuckle joint presses are also possible to use for press fit process, depending on the force needed. The presses with a force sensor combined with a software that shows a force displacement diagram are optimum. They offer the possibility to immediately evaluate the quality of the press fit process. And a very important aspect of this whole technology is not to add too much speed to reach a homogeneous connection between the pin and the via. Impact pressure would deliver a spiking stress on the pins on the PCB, and the connection might not be done in the correct way. So you might detach some of the plating on from the PCB, and that is not desirable. So let's check the video here. And this is the connection is very important and pressure. So the constant pressure. So the different types of knuckle joint presses are possible to use for the press fit process depending on the force needed. So the presses with a force sensor combined with a software that shows a force displacement diagram are optimum, and they offer the possibility to immediately evaluate the quality of the press fit process. and so there will be a better quality on the finish, and mm, the connection would work better. And so uh, some application examples can go from what I showed you before, a very space-saving design uh, and very space-efficient design. Then the high power with protective insulation on an enclosure. So maybe a waterproof enclosure, maybe using two red cubes to keep the wire in the desired direction, as you can see on the image on the top right. Then a mount for a high powered fuse that could be really useful for high power applications. Then the pressing a bus bar layered on a PCB, so this would transmit a lot of current, much better transmission of current than just a layer of copper inside the PCB. So this would have a little bit of heat dissipation and increased efficiency. And for the last image, we could see a power delivery on stacked PCBs. So this could even work as a spacer. And so thank you very much. I can answer the questions. Let's see the chat for any questions that you have. So we have a question that says, does REDCUBE can be used with the ENIG board? And the answer is yes, it can be used with that board. So there is also another. So there is also another question. Are there development kits available? Yes, there are. There are kits available for uh, development that you can use for your application. So there is another question that says, are the REDCUBE massive press been certified for automotive? So it isn't suggested to use the ICS automotive division for those applications, but yes, the design is possible in those kind of applications. So let's just wait for some more questions in here. So we have another question that says, for a stacked PCB, is there some REDCUBE available with press fit on both sides? And yes, it is suggested that both sides have a press fit used to make the junction. So if you were to connect those stacked PCBs, it's better to connect them both with a press fit connection than with another type of connection. And so the two-part system will allow a maximum tightening possible. So it would be a good solution for the application. Okay, so we have an interesting question. It says, I don't understand how adding a solder to a pressit connection makes it worse. Can you speak to this a little bit more? And yes, so what I was mentioning was that adding the process itself of adding the solder to the REDCUBE connectors is something detrimental to the connector itself. So the tin plating could be damaged, and so the tin could flow to another part of the connector and make it worse. And also the other part, the other really important so to the rest of the PCB, other components could be damaged with the really big heat source. So we have another question here as well that says, can the REDCUBE be disassembled if needed from the PCB? It says it can be removed within a short amount of time, but not suggested because the via is deformed. So you already have a deformation inside the PCB. So it could be removed, but it is not suggested. And so after a long time, a long resting time, the cold welded joint would be fully bonded. So I said before that 48 hours maximum for the welded joint should be necessary. So onto the 48 hours, there will be a complete joint between those two components. Before that time, could be possible to remove, but there would already be a plastic deformation, a permanent plastic deformation. Yes, there will be a so just to clarify, there would be a deformation on the via, not on the connector itself. And so, well, thank you very much for attending the webinar. We really appreciate all your time spent listening to this webinar. And well, thank you very much, and we hope to see you in another webinar.